Okay, let's look at the statement and proof of Theorem 14. So Theorem 14 says that we have a function f and it's defined on a subset of R2. And the subset is actually going to look kind of like this. And our f is continuous. And we know that the partial of f with respect to y exists and is continuous. So this statement right here is telling us that the mapping that would take y and send it to f of x comma y is a C1 mapping, okay? So the conclusion is that this function, which is defined, f of y is defined to be the integral of little f as x ranges from a to b. So the picture of that would be fix a y, and you're going to integrate your function over this line segment. So that function that sends y to the integral of f over that line segment is of class C1, and its derivative is the integral of the derivative of little f with respect to y. Okay, so this is important. Again, we are interchanging limits because when we're computing the derivative of f, we're computing limit of limit, right? Because integral is a limit, and by the way, we're using Riemann integration here. So computing this derivative involves interchanging limits of the derivative with limits resulting in the integral. Okay, so let's go ahead and get started. Notice we have two conclusions, right? So the first conclusion is that our big F is exists and has this, or the derivative exists and is equal to this. The second conclusion would be that the derivative itself is continuous. So on this slide here, I've just rewritten the hypotheses so we can look and see, verify that I haven't missed anything. So I have my F, the domain and the codomain. F is continuous. The partial of F with respect to Y exists and is continuous. And big F is defined like so, okay? And then the claim, big F is of class C1 and big F prime actually is this integral. So for the proof, we're going to again have two steps. Step one is going to be to show that f prime of y exists and equals this integral. And then step two, let's say step two over here, is going to be show that f prime is continuous. Okay, so let's go back to step one. How do we show that the derivative exists? Well, notice that big F is a function that is defined on this open interval CD. So big F actually goes from CD to R. So when we're computing f prime, we're literally going to just look at the limit as h goes to 0, big F of y plus h minus big F of y divided by h, okay? So let's go ahead and do some estimates on that difference quotient. Okay, so we'll say fix y belonging to C comma D. Then f of y plus h minus f of y. And first of all, I guess we should make it clear that h needs to be small enough to guarantee that y plus h is in the domain of big F. So we can say, so for small h, this is going to be equal to, this difference quotient is going to be equal to, I'm going to go back to my definition of f of y. So f of y is defined as this. So f of y plus h just means I'm going to integrate over the line segment that you get at y plus h. So I'll have the integral, well, first I can pull out the 1 over h, okay? Then I have the integral from a to b of f of x comma y plus h dx minus the integral from a to b f of x y dx. Okay, and there's nothing special about keeping these integrals separate since the domain of integration is the same, right? Since we're both integrating from a to b, I can combine these and write it as 1 over h, integral a to b, f of x y plus h minus f of x y dx. Okay, and notice that it's okay to even define big F because my little f is continuous, and we know that continuous functions are Riemann integrable. Okay, so here's where I'm going to use my mean value theorem, my C1 mean value theorem, because for every fixed x, remember, this function is C1 in the y variable. So I can use my C1 MVT. And let's see if we can, let me add a page here. And let's see if we can put it in right quick. Here we go. So recall, if your function is of class C1 and the line segment is contained in U, then we've got this. So what I'm going to do is, for the function I'm going to apply it to is the function that takes y and sends it to f of x comma y, right? So the function, my function is y being sent to f of x comma y. This is C1 by hypothesis. The line segment that I'm integrating over is from y plus h, from y to y plus h. Okay, so back in the picture here, y is some point in between C and D, and h is small, so maybe that's y plus h. And I'm saying if I want to integrate f over this line and f over that line, I can actually look for any fixed x and look at the difference between f here and here, right? And use the fact that along this line segment, my f is, f restricted to this line segment is C1. So if I want to know the value here minus the value here, I can use my C1 mean value theorem, okay? So what am I going to get? I'm going to get, let's see here. The U in this case is the open interval CD, right? I'm going to get that my f of p minus f of q, so that is going to be y plus h minus f of x, y, right, is equal to t. So this is supposed to be the average derivative of y being sent to f of x, y along the line segment from y to y plus h, okay, times p minus q, this minus that is going to end up just being h, times h, okay? So if I go to highlight these different quantities, this is the h, the t is right here, and of course, the yellow is the most straightforward, okay? So now let me break it down a little bit more, because what is the average derivative of f along the line segment? Well, that's just going to be equal to the partial, the average derivative. So I'm going to add up. I need the partial of f with respect to y at this point right here. So if I have p plus t times q minus p, and my p is y, and my q is y plus h, this is going to end up being y plus t times h, right? Because q minus p is just y plus h minus y. So I just end up with y plus th. And now my partial, or my derivative, is going to end up being the derivative of this function, right? Remember, this is a one-dimensional function. It's going to be the partial of f with respect to y. So I'll have the partial of f with respect to y evaluated at the point, and we said it was going to be y plus th, and then this dt. So this is my average derivative, yeah? Okay, so I've got that times h equal to this. So I take all of this information, let me resize. Yeah, so this is true for a fixed x. So I need to go back here and continue with rewriting my difference quotient. So let's see here, paste. So we'll have this equal to 1 over h times the integral from a to b. Now I'm going to replace this, right, with this average derivative times h, okay? So I'm going to have the integral from 0 to 1, the partial with respect to y, f of x, y plus th, dt, and then don't forget I have that factor of h. Okay, times h. Okay, so now I step back and I notice that this h has nothing to do with x, so I can pull it out, right? And this h and this 1 over h will cancel each other out. So I'm actually working with just the integral from a to b of the integral from 0 to 1, the partial of y, partial of f with respect to y at x, comma, y plus th, dt, dx. Now I use the fact that my partial of f with respect to y is continuous to say that as h goes to 0, this is going to approach just the partial of y with respect to f at partial of f with respect to y at xy. right? Since f is continuous. So when I take the limit as h approaches 0 of the left-hand side, it'll be equal to the limit as h approaches 0 of the right-hand side. This integrand here is going to the partial of f with respect to y. And because we are on this bounded set, we're going to have bounded compact set, right? So x is in between a and b, t is in between 0 and 1, so we'll get a rectangle here. So this is going to how do I write this? Let's see here. So since the partial of f with respect to y, y is continuous, the right-hand side this is going to approach just the integral AB, integral 0, 1, xy, dt dx as h approaches 0. Okay? So big F prime of y is going to equal this. And what is this? Well, the dt, or if I integrate this with respect to t, I'm just going to get the partial of f with respect to y. So let's add a page in here. So f prime of y, which is the limit as h goes to 0, for y plus h minus big F of y over h, is equal to this, which is equal to just the integral a to b okay. So we're done with this first step. Show that f prime exists and equals this. So we're done. So we have completed step 1. And what remains is just to show that our f prime is continuous. So our f prime, we said f prime of y is this. Well, this is going to follow that big F prime is continuous, follows from the fact that the partial with respect to y of fy is continuous. Okay, so here's what we're going to do. Fix y or y naught in CD. Let epsilon greater than 0 be given. And we wanted to show there exists a delta greater than 0 such that y minus y naught, if that distance is less than delta, that implies that big F prime of y minus big F prime of y naught, that distance is less than epsilon. Okay? So let's go back and look at what is our big F prime of y. Here's our formula. So I'm just going to, in pink, so our goal that this implies this minus the integral from AB partial y little f x y naught dx, that is less than epsilon. Yeah, so this is our goal. Okay, this is our goal. I'm going to combine these integrals because they're both integrals with over AB, okay? So that's what I want, okay? I say, aha. I know by the triangle inequality for integrals that this integral is always less than or equal to the integral of the absolute value of the integrand. So maybe if I can get this to be less than epsilon, then this will be less than this will be less than epsilon, and I'm done. So let me show. So this partial here minus this partial is always less than or equal to. I'm actually going to copy and paste. Now I'm just literally going to slide the absolute values on the inside. Yeah, so this is by triangle inequality for integrals. Okay, now I can make this as small as I want because my partial of f with respect to y is continuous at y naught, right? So I can make this less than or equal to say if I make this less than or equal to epsilon over b minus a, and now this is going to equal epsilon, yeah? So I'm going to say, since, here's what I'm going to do. I'm not going to write it out because it's long. What I'm going to do is I'm going to say, since my partial of f with respect to y is continuous, there exists a delta such that y minus y naught, that distance less than delta, implies this is less than epsilon over b minus a. So then the integral of this is going to be less than the integral of that, which is going to be less than epsilon. So then this, which is less than or equal to the integral, is less than epsilon. Okay? So that's how my argument's going to go. So let's go ahead and write that out here. Since the partial of f with respect to y is continuous, there exists a delta greater than 0 such that whenever this is less than delta, that implies the partial, the values of the partial are less than epsilon over b minus a, okay? But that's going to imply that the integral of this is less than the integral of this, and then we're integrating from a to b with respect to x. This right-hand side is just going to be epsilon, yeah? We'll say, but the triangle inequality for integrals implies the, okay, this is less than or equal to this so the result follows, right? In other words, for this delta, when this is less than delta, that's going to imply this is less than or equal to this, but that is less than epsilon. Okay, so we're done. All right. As usual, please let me know if you have any questions.